things can go. Okay? So where we're going to spend the rest of our time today pretty much is talking about intermolecular forces in specific. Okay? And we'll talk about the different types and how we can talk about their strengths. But first, let's not forget, where do intermolecular forces exist? Between atoms? Between molecules? It's a little better. Okay. So again, nice little picture. Here's a water molecule. Here's another water molecule. Okay. Draw a little oval around it so you can see that those molecules are sort of acting as units, but it's the intermolecular forces that attract a molecule to its neighbor. Okay. What are the forces that hold a molecule itself together? I heard somebody say something. What is that line between the O and the H inside of a water molecule? It's a bond. What kind of bond? Yeah, covalent bonds are inside of molecules. Okay. The intermolecular forces are between. Okay. Covalent bonds are much stronger. Okay. It's not too difficult to just separate two water molecules from each other. Okay. It's actually very difficult to destroy a water molecule, okay, to rip one of the atoms right out from the inside of the molecule itself. Okay. So don't forget that. I'm going to ask you that a couple more times today, so be ready. We are going to learn about the three different types of intermolecular forces, and they appear in different circumstances, so we need to know how that works, and we can also talk about how strong they are relative to each other, and maybe how strong they themselves can be. So we're going to start with dispersion forces, sometimes called the London force, named after a scientist that had a lot to say about this, London. So dispersion forces are present between all molecules. Okay? So it's sort of the default intermolecular force, okay? And in between doesn't even need to be molecules, really. These are just atoms of helium. Helium is atomic, okay, in that it doesn't really form compounds. It's a noble gas. So it doesn't really form chemical bonds with other atoms to make molecules or compounds. It's just helium. Pretty much those atoms are fine hanging out on their own. But there is some attraction even just between those atoms. Okay? So really anything with a cloud of electrons has dispersion forces. And it's kind of interesting how they work because it takes advantage of some of the properties that electrons themselves have. So these are just sort of three frames. Okay? A helium atom has protons in the nucleus and then 2 electrons flying around. Okay? That's just what a neutral helium atom is. And those electrons are flying around all over the place, just randomly. It could so happen that at one point in time, the 2 electrons are over on this side, just totally randomly. But what that means is at that point in time, this side of that atom is more negative because the electrons are over on that side. Okay? This side is a little more positive because there are no electrons here, and what we're actually seeing is the nucleus. Okay? The nucleus has protons in it that make it positive. Okay? But just after that, those electrons could be flying all over, okay, in other places. But what's important about this is that at that instant in time, that becomes temporarily polar. This is a temporary dipole. Temporary just meaning it's only there for a short period of time. Okay? And these arrows always point towards the more negative side. Okay? So there's more electrons over on this side than on that side just due to random chance. Okay? But then the interesting thing happens. This middle one in here, that's our original temporary dipole, just like we had up above. Okay? That just due to random chance, we've got electrons over here. The interesting thing happens when we have a molecule or atom nearby, when one happens to have a temporary dipole. So what's going to happen over here, the electrons in this nearby atom are going to respond to that temporary dipole. Okay? So this is the more negative side, okay, of that temporary dipole. These electrons here themselves are negative. So what do like charges do when they get close to each other? Like charges repel, right? Opposite charges attract. So see, these electrons just randomly are over here. So the electrons in this atom, they got repelled. Okay? Electrons repelled. And similarly, the electrons in this one over here, they actually got attracted over to this side. And they're attracted to the partial plus side of that temporary dipole. Okay? So again, if we have an atom that just randomly has its electrons over on one side, the atoms or molecules nearby, their electrons will actually move in that similar direction to that original one. It's kind of interesting, okay? Because if we're heavy over on the left here, like that, it's going to push these ones away, move them over to their left, but it's also going to attract the ones over here because they're actually being sort of attracted to this bare nucleus that doesn't have electrons on that side of it. Okay? So the dipoles tend to sort of align with nearby molecules. Okay? We end up with what's called an induced dipole on the neighboring atoms or molecules. Okay. And because now we have a whole grouping of molecules that have essentially become polarized, right? They sort of have a plus side and a minus side. They will actually start to attract overall. Okay? Think of now this atom overall that has a plus side and a minus, and that one has a minus side. Okay? That overall is going to be attracted to this one. The atoms attract. Okay? Same thing with this one. Those are the dispersion forces that we were talking about. Okay? So it's a two-step process. All we need is one that randomly has its electrons on one side. Its neighbors, their electrons will move that same way because of the way electrons work. Okay? And then that causes the atoms overall to pull together. Okay? Because we end up with negative sides and positive sides to them. They become sort of like little magnets just because of that. Okay? So it's a really interesting thing. It's not something you would originally expect, just having all negative electrons, okay? But it's just sort of a side effect that electrons are orbiting around a positive nucleus, that if all those electrons move the same way, the atoms actually attract. Okay? So that's why we said that dispersion forces are present between all molecules, atomic elements too. Anything with an electron cloud will have this kind of random interaction that'll cause those electron clouds to be attracted to each other. Okay? Anybody have any questions about that sort of two-step process that makes dispersion forces? Okay? Now, what we can do, we can use dispersion forces to make some comparisons between different types of molecules. Okay? We can actually estimate their strength by calculating a molecule's molar mass. Okay? just because the larger a molecule is, the more massive a molecule is, the more electrons it has, and the more chances there are for these interactions to happen. It's just sort of a statistical thing. Okay? So what we can do, though, we can compare iodine, bromine, and chlorine. Okay? We can estimate the strength of their dispersion forces just by estimating their molar mass. And where do you have to go to look at molar masses again? Yeah, that was a little bit ago, periodic table. This, you really don't need a calculator to do this, just a close estimate. But iodine, 126, I mean, we could even call that 127 for just I. Okay? But because it's I2, you have to take 2 of those, okay, for the molecule. So let's just do 254 right here. Let's say approximately 254. But remember, it's I2 because diatomic molecules have 2 atoms covalently bonded together, right? Br2, Cl2. Okay. So 254, 160, 70. Okay. So which one of those would have the strongest dispersion forces between its molecules? Yeah. Strongest to weakest in order. Of these, at least. Okay. And remember, what we're talking about here are actual interactions between one iodine molecule and its neighbor. Okay. Dispersion forces are present between all molecules. Okay? So we're not talking about that being attracted to that. We're talking about a sample of iodine and how strongly iodine molecules are attracted to their neighbors. Okay? So the largest molecule will have the strongest dispersion forces, but we can go a little further than that. We can estimate boiling points just from that. The boiling point is the temperature where a what becomes what. Okay, got that. And remember, for a liquid to become a gas, those liquid molecules have to get moving fast enough that they can pull apart from each other and fly away. So if a substance has relatively strong intermolecular forces, if those molecules are held fairly tightly close to each other, that substance would have a relatively what? Low or high boiling point? Think about that. Because remember, you have to crank up, you have to keep turning up the heat until the molecules get moving fast enough that they can pull apart. If they're stuck really strongly together, you're going to have to keep turning up the heat higher and higher until they get moving fast enough to pull apart, right? So substances with relatively strong intermolecular forces will have a relatively high boiling point. So which of those 3 do you think will have the highest boiling point? Absolutely. Iodine will have the highest, okay, because I2 has strongest dispersion forces in between its molecules, and we estimated that by molar mass. I'm just going to say mm. Okay. And the lowest boiling point of those 3? What do you think? Strongest dispersion forces. That meant that we needed the largest amount of energy, the highest temperature for it to boil. Okay? Boiling point will follow this same progression right there. So the chlorine would be the lowest, okay, just because of its weakest dispersion forces. And I chose these 3 as an example because it's actually pretty dramatic. At room temperature, iodine is a solid Bromine is a liquid. Chlorine is a gas. Okay? So think of that. If the liquid and gas ones are the easiest to think about because if something is a liquid at room temperature, that means its boiling point has to be higher than room temperature, right? We'd have to heat up a liquid to get it to boil. But if something's a gas at room temperature, that means its boiling point is lower than room temperature. It's already, room temperature is enough for it already to have boiled, right? If something's solid, that means we have to heat it up and then it has to melt first and then it has to boil. Okay? So it has to pass through the melting point and then the boiling point. Okay? Sometimes it sublimes, but go ahead. Yeah, absolutely. Yep. It can condense into a liquid, and even things like helium can freeze. Okay? It'll take like 2 or 3 Kelvin or something like that, but yeah, if something has any kind of intermolecular forces at all, we can conceive of a temperature that would be cold enough for them to lock into place. So. All right, so don't forget, we can use dispersion forces. Okay? We can estimate their strength using molar mass. And if dispersion forces are the only thing we're comparing, we can relate that to boiling point. Okay? So remember, dispersion forces are present between all molecules. That was sort of number 1 on our list. Dipole-dipole forces are a different intermolecular force. They're attractions between opposite dipoles of polar molecules only. Okay? So if we have a polar molecule, everything has dispersion forces, but a polar molecule now also has these dipole-dipole forces. So let's draw a quick polar molecule here. Let's draw HCl. It's a polar molecule, right? And it's polar because chlorine is more, what do we call that property that determines how strong an element pulls? Chlorine is more electronegative. Yep. So we get a partial negative on that side, partial plus on that side. What's going to happen if we get a neighboring HCl molecule? It'll look the same. Plus on the H, minus on the Cl, has a dipole like that. These molecules overall will now be attracted. The negative side will attract to the positive side of that. Okay? This is the dipole force. It's called dipole-dipole because the dipole of one will attract to the opposite dipole of its neighbor. Okay? Polar molecules, we've talked about this before, polar molecules behave like little magnets, okay? Where opposite sides will attract. Okay? If the same sides approached each other, they would repel, and one of them would probably flip around so the opposites could attract, okay? Like that. Okay? So the fact that these are polar molecules, they have dipoles that are always in this direction. Okay? The little dipole arrow is always going to be pointed from the H to the Cl. Okay? Compare that with our atoms that we had up above. It was just totally due to random chance that this one happened to go this way. Okay? In another moment, any one of these could have flipped to the other direction, and all the ones around them would have flipped in response. So they're all kind of flipping all sort of together within a region. Okay? But we called that a temporary dipole because it was just due to random chance, where here in a polar molecule, this is the opposite of temporary. What do you suppose we would call that? Permanent. That is a permanent dipole. Polar molecules, they don't have temporary dipole. I mean, they have some dispersion forces. There's some randomization of that happening. But they're sort of dominated by that permanent dipole that's always in that direction. Okay? So sort of in addition to the dispersion forces. So if our molecules are polar, we have to think about dipole-dipole forces. The reason we could get away with just doing dispersion forces on these molecules on this last page is that these were all nonpolar. Okay? if a molecule has no permanent dipole of its own, the only attractions between them will come from those dispersion forces. Okay? So nonpolar molecules will have dispersion forces only. Polar molecules will have dispersion and dipole-dipole. That makes sense? So now we can start comparing boiling points of slightly more complicated molecules. We've used CH2O several times as a reference. I mean, it's clearly going to have the two H's attached to the C, right? Because carbon has to make 4 bonds. So how's that C going to be attached to the O? Double? Okay. So let's compare CH2O versus CH3CH3. And I'm just going to draw these out. Okay. Now, to compare the boiling point of molecules, we have to consider all the possible intermolecular forces within a sample of that molecule. So we're going to start with dispersion forces, like before. Okay. And what did we use to estimate the strength of dispersion forces? You got it. So H is just 1, right? Carbon 12, N 14, O 16. That's going to get you by with most organic molecules, right? So 12 for the carbon, 2 more for the H's, so that's 14 plus 16 for the O, so that gives us about 30. A molar mass of about 30. Okay. Here we got 12, 13, 14, 15 times 2, right? Molar mass of about 30 as well. So what do you suppose that tells us about the strength of the dispersion forces in samples of those two molecules?
Around the same.
Yeah, let's say similar dispersion forces. We cannot say that they are identical, because remember, molar mass is just an estimate, but we can say they're similar. They're close enough that we can't tell a difference with this method, at least. Okay. But then we also need to consider dipole-dipole. Just going to say dp-dp there. And dipole-dipole forces will only show up if the molecule is what? Polar. You got it. So is the CH2O molecule polar? What do you think? Yeah? We'll have an arrow that's pointing towards the what atom? Towards the sky? Sure, that works. I was thinking towards the O, but yes, it's also pointed towards the sky if we draw it that way. Sure. Okay, but that's because O is more electronegative than C. Okay. If I had drawn that the other way, it would be pointed towards the ground. What do you think about polarity of CH3CH3? I told you something special about carbon and hydrogen. Yeah, carbon and hydrogen have similar electronegativities. We don't draw arrows between C's and H's. Okay? They share their electrons equally. So if this one is polar, this one is non-polar. And in fact, all hydrocarbons are nonpolar. So really, we didn't even need to draw that one out. If it just contains C and H, it's nonpolar. Okay? There's no way to make arrows that align in one direction. So dispersion forces don't tell us much in this case, but the fact that one molecule is polar versus the other nonpolar, which one of these do you think will have the higher boiling point? You got it. Boiling point. Let's do purple again here. Boiling point, higher. Boiling point. Let's just say higher, BP lower. Okay. The addition of dipole-dipole forces to that polar molecule will be something else that's pulling those molecules towards each other, okay, which will require a higher temperature to pull them apart to separate them. Okay? Leave those things up there. You guys saw something like this when we did the soap lab before. Polarity is what determines a property called miscibility. That's whether or not two liquids will mix. Miscible liquids will mix together in any proportion, but immiscible liquids will not. So if we have a combination of two liquids with different polarities, like water on this bottom layer, or some kind of oil on this top layer, that to me looks like hexane, C6H14 from its structure. Okay? But any oil would be usually a hydrocarbon. Okay? What's water's polarity? Polar or nonpolar? Yeah, water is polar. It's a very important property of water because of that bent shape, right? Oils, any hydrocarbons like that are nonpolar. So opposite polarities like that, they will not mix together. Only substances with similar polarities will mix. Water and ethanol will mix totally and completely with each other because they're both very polar. Okay? But water and hexane will not at all. That's the exact same reason here's some oil on top of vinegar. Vinegar is mostly water. Okay? So same sort of thing with the two substances not combining. There's a picture of an oil spill. One way that they clean up oil spills is to drag those big booms around. They're big ropes. And it sort of corrals all the oil that's floating on top of the surface. And obviously that wouldn't be possible if oil and water mixed. Okay? But due to the fact that they're different in polarity, some of it at least will float on the surface and can be skimmed off and collected that way. Okay? So another way of saying this, we saw that again in the soap lab. Like dissolves like. Now, we can get around that. We can get oil and water to actually mix together, say if we want to clean it up. If you got some oil or something greasy on your hands or your shirt and you want to clean it up, we can use something like a soap or detergent. But what's special about the polarity of soap molecules? It's both. It's polar to attract to the water. It's nonpolar to attract to the oil. And it actually collects it up in those micelles that we talked about before. Okay? Sort of hides the nonpolar thing in the inside of it like that. So, alrighty. Let's do another comparison right here of acetone and water. I'm going to draw the structure of acetone for you. You guys used acetone to clean out the test tubes after the stinky ester lab, right? So it's an excellent solvent. This is what its structure looks like. It is a CH3 C double bond O CH3. Okay, that's acetone. We can compare that with water. Remember, whenever we're talking about polarity or anything, it's important for us to draw the two single bonds to an O as bent, like that. Otherwise, we might get the wrong idea about the polarity of that. Okay? So, estimates for molar mass, I got 58 for that one. That's 15 for the CH3, and so 30 for the CH3s. 30 and 12 and 18. 30 and 12 and 16. That's 58. Okay. So 18 for water. So which of these, acetone or water, which of those has stronger dispersion forces? Yeah. Stronger. Weaker. So looking at the molar mass, that determines dispersion forces. But a very common mistake that students make is to sort of stop at that step. Okay? Remember, we've seen 2 of them so far. There are actually 3. We have to consider all of the possible intermolecular forces, okay, within samples of those substances. Okay? So let's talk polarity. Do you think that acetone is polar or nonpolar?
Polar.
Yep, we got a we got a more electronegative O pulling away from the C. No arrows on the CC bonds, no arrows on the CH bonds. Okay, so polar. That means a yes to dipole-dipole forces, right? What about water? What did we say its polarity is? Polar or nonpolar? Yeah, definitely polar. We have polar bonds, okay? Two of them within the molecule, but don't those cancel each other out? No, they do not. Because why? Yeah, because they're at an angle. They're bent. Okay? That adds up to an upwards pointing net dipole moment. Water's polarity is one of its most important properties. Okay? So if dispersion and dipole-dipole forces were the only thing here, the dipole-dipole forces don't tell us much because they're both polar. Okay? Dispersion forces might lead us to think that acetone would be higher boiling. Okay? But look at the actual boiling points. Acetone 56, water is 100. So there's something else here pulling those water molecules very tightly towards each other. Unusually so for a molecule that small. Okay? It's actually very strange for a boiling point of 100 on a very small molecule like water, something with very weak dispersion forces. So we got to move on to our third intermolecular force. Right? Way back here, said there are three types of intermolecular forces. Dispersion forces present between all molecules. Dipole-dipole forces present between polar molecules. Yeah, you can go back to that page. It's not, wouldn't be a bad thing to write that. Polar only. Why not? So everything has dispersion forces. If the question is implying, does this molecule have dispersion forces or not? The answer is yes. It has dispersion forces. Okay. Only polar molecules have dipole-dipole forces. Okay. And the last one, which must be involved here, is hydrogen bonding. Okay. One of those molecules, acetone or water, has hydrogen bonding, an extra strong dipole force resulting from what we'll call an electropositive H. So to find this electropositive H, we need to look inside of the molecule for one of these bonding patterns. Okay? An NH, an OH, or an FH inside of that bond. And the reason those are special is because NO and F are the three elements that can most strongly pull electrons away from an H. Okay? And what we end up with is a very strong partial positive on that H. Almost a full plus, in fact. Because think of a hydrogen. Okay? A hydrogen, just on its own, would be a proton and an electron. Right? Hydrogen is number one on the periodic table, so it would be a proton and an electron. When hydrogen is bonded, its one and only electron is in part of that covalent bond there. Okay? So when something pulls that away, its one and only electron is getting pulled away from it, and all we see sort of is that proton in the nucleus that's kind of left out there exposed. Okay? Other atoms, if they get electrons pulled away, they at least have some of their own that they get to keep around them. But hydrogen's one and only electron is in that bond and getting pulled away from it. Okay? So, remember we're looking for NH, OH, or FH. Look inside of those molecules. Which molecule, acetone or water, has hydrogen bonding? Water does, because right here, here's an OH bond. Let's give it a partial plus strong And here too. Okay. The little row we can add here, hydrogen bonding, no, hydrogen bonding, yes. All of these H's are attached to C, so nothing too special about that. But if we have an H attached to O, that's going to make this extra strong as a partial plus. Okay? But then, let's draw a little molecule here. Let's draw water down here, make it nice and big. Okay? Draw those partial plus strong. Okay? And let's look at this one right here. That's an extra strong partial plus. What is that going to be extra strongly attracted to? The O atom? Which O atom? This O atom? The covalent bond is what attaches that H to the O atom. Okay? That's just a pair of shared electrons right there. Okay? And those electrons have been pulled over this way. That's what's made that plus so strong. So what is this plus actually going to be attracted to? Think about this. Let's answer this question. Hydrogen bonding, it's like all the other intermolecular forces. And where do intermolecular forces occur? Between. Okay, there we go. We drew this picture up here before, just in general saying intermolecular forces happen in between molecules. We can be much more specific now in saying that the hydrogen bonding means this H is going to be very strongly attracted to what? It's going to be a real strong attraction between this H and what over here? The H? The H on the other molecule will be plus as well. So what's it going to be? There we go. So draw another water molecule here. Okay. Remember, these O's are partial negative. Okay. Here is hydrogen bonding. Okay. This is a real common point of confusion that I'm sure I will ask the heck about on the exam. So, and you know, it's if you have careless thinking, right? A lot of it comes from the fact that you're looking inside the molecule to find an NH, OH, or FH, but those are not the hydrogen bonds. That's not the hydrogen bonding. That's just finding the extra strong partial plus H, the electropositive hydrogen that we talked about. The actual interaction is between that H and the minus of a neighboring molecule. Okay? Because remember, we're talking about boiling points here. We're talking about having a water molecule and being able to pull its neighbor away from it. Okay? When we boil water, we're separating water molecules. We're not destroying the water molecules. We're not pulling the water molecules themselves apart. We're just pulling them apart from their neighbors. Okay? So that's where the hydrogen bonding happens. Okay? An extra strong partial positive with the negative of a neighboring molecule. Okay? And that's super, super important right there. Okay? So that ended up actually making the difference, hey, for the boiling point of that. Even though dispersion forces were sort of the other way, dipole-dipole forces didn't tell us much. Just the fact that we have hydrogen bonding, look at the huge difference that it made in the boiling point of water compared to acetone. Okay?